Welcome to solverfy.
Okay, so problem 38 gives a series of decays and wants to know if they're possible, and if they're not, why not? So let's look at part A here first. So part A gives this particle, which is this neutral particle, and that decays into a sigma plus a minus pion. So first, let's go, in order to verify this, we just need to check all the conservation rules. So let's first start with charge. So charge, this guy is 0, is equal to plus minus 1. Since that's positive, that's a minus, so charge is conserved. Now let's look at baryon number. All right, so baryon number, we have 1, because this guy's a baryon. Sorry, that's not plus, it should be equals. Equals to 1, because the sigma is a baryon. Plus 0, because the pion is not a baryon. So that is conserved. 1 is equal to 1. All right, so now, lepton number. We have 0 is equal to 0 plus 0. All right, now finally, let's look at the strangeness number. So this particle is very strange. It has a -2 strangeness. The sigma has a 1. The sigma plus has a -1. Plus 0. So this is not conserved. But that doesn't necessarily mean it's not possible yet. Determines whether or not mediated by the strong force, strangeness has to be conserved, but this still could be possible via the weak force. Now, the final thing we need to check, though, is the mass energy. So for the mass energy, we have to check the Q. So the mass energy of this guy is 1314.9 MeV per c squared, minus the products here, so 1189.4 MeV per c squared, minus 139.6 MeV per c squared. Now, all right, so let's just work this out. So that's equal to minus 14.1 MeV per c squared. Okay, so this reaction is not possible because decay. So it needs some extra energy in order to make it possible, and since this is just a decay, we assume this particle is at rest, or we don't even assume it. Yeah, it's decaying, so there's no collision going on. So there's no added energy. So conservation of mass energy does not hold up. So this decay is not possible. So now for B. So B gives this reaction. The negative omega goes to this neutral sigma plus the minus pion plus a neutrino. So now we need to, again, check our conservation laws. Let's look at charge. So we have 0. Sorry, -1. -1 charge on this side. That's going to be equal to 0 charge for him. He's neutral, plus -1 charge plus 0 charge. All right, so -1 is equal to -1, so charge is conserved. So now for baryon number, we have plus 1 for the omega is equal to plus 1 for the sigma, plus 0 plus 0. So that's also conserved. So now we have lepton number. So we have lepton number. We get 0 is equal to 0 plus 0 plus 1. The neutrino is a lepton, so this is not conserved. Therefore, this is not possible. This is forbidden because the number is not conserved. Now for C, we get the decay. We have the neutral sigma decays into the gamma. It's not gamma. This particle plus a photon plus another photon. Now, so let's look at the conservation. Charge, we get 0 is equal to 0 plus 0 plus 0. So that's conserved. Baryon number, get 0 is equal to 0 plus 0 plus 0. So that's also conserved. And then we have, let's see, lepton number. 0 is equal to 0 plus 0 plus 0, so that's conserved. Strangeness. This thing can be hard to write with sometimes. Sorry about that. Do better. Strangeness is going to be, minus 1 is equal to minus 1 plus 0 plus 0. So strangeness is also conserved. So now let's check mass energy. We have 1192.6 MeV per C squared minus 115.7 MeV per C squared plus 0 because there's no mass to a photon. So you can already see that this is possible, but this comes out to 76.9 MeV per C squared. So this is possible. And since strangeness is conserved, it's possible via the weak force. I'm sorry, the strong force. All right, now part, let's see, is that, yeah? Oh yeah, we just get those three. So